Hi everyone, welcome back to Physics 142. In this video, I want to combine a couple of the things that we've been talking about by considering the forces that happen between two wires, two parallel wires. All right, and so the setup that I want to think about here is I want to think about, all right, if we have some wire and we'll have some current I running through that wire, all right, and then I want another wire here, and in that wire, I'm going to have some current, I'll call it I prime, all right, to indicate that it's potentially a different amount of current. And let's take these two wires and let's separate them by a distance capital R, all right? We'll separate them by a distance capital R. And the question that I want to ask here is, I want to know what is the force per unit length, all right, of one wire onto another wire, all right? And to be sort of concrete here, all right, let's say we want the force per unit length from wire 1 onto kind of wire 2 here, right? From the I wire onto the I prime wire, how much force does it generate? And to think about how this is going to work, right? Well, current 1 here is going to be generating a magnetic field, right? If you have some current running that's going to create a magnetic field, we can use the Biot-Savart law to think about what that magnetic field will look like, right? And you might, recall that we've determined from Biot-Savart that if you have a current, the magnetic field around this wire is going to loop around this wire, right? So what we'll get is that on top of this wire, we'll have a bunch of magnetic field coming out of the board page here, right? And we'll have a bunch of magnetic field going into the page on this side, right? The magnetic field is sort of looping around this wire, right? But if you're creating a magnetic field, well, this wire is going to have some charges which are moving in that magnetic field, right? And if you have charges moving in a magnetic field, right, that's going to create a force. So wire 1 will create a force on wire 2, right? But, well, we also know that wire 2 is going to be generating an electric field, a magnetic field, because it has moving current, and that will create a force on current 1, on wire 1 here, right? And we know from Newton's third law that those two forces will be equal to each other, and so, the force per unit length between the two wires, that's what I'm interested in, right? What is that force? Well, let's also think about what would the magnetic field for I prime here for wire 2, right? I guess I should label these. I'm calling this one wire 2, this one wire 1, all right? Well, this one, again, will have magnetic field coming out of the page on the top, right? And we'll have magnetic field going into the page on the bottom, right? So it's also generating a magnetic field. And we can calculate how much magnetic field is getting generated by the wires, right? Equals question mark, right? That's what we're going for. So how much magnetic field is getting generated? Well, we can calculate that from the Biot-Savart law. If they have constant current, then that will come outside the integral, and we'll have the integral of dl cross r hat, right? Divided by r squared. And we worked out for really long wires, right? For long straight wires, you can check some other videos, but we got an answer that it's mu naught times I divided by 2 pi r, right? That's the magnitude of the field produced by wire 1, right? If I replace this with an I prime, that would give us the magnitude of the field from I prime here, right? Okay, so that tells us how much magnetic field you have. And if we think about it, right, then we can use that magnetic field to calculate how much force there is. Well, how do we do that? Well, we need to know the force law. And so we think back to our Lorentz force law from earlier, right? Our what we learned about forces. And remember, we had a couple formulas for forces. One of them was QV cross B, right? Depending on the speed of the charges moving. And for a wire, we also noted that that was I times L, the length of the wire, cross B, right? So for wires, we're able to write it in terms of current. And if we're thinking about the force on I prime here, then maybe I should just go ahead and throw I prime into the formula, right? And so now we're ready to actually figure out what this force is. So, well, okay, so what is it? So it's the amount of current, I prime, times the length of the wire, we'll just call that L for now, times the strength of the magnetic field, well, the strength of the magnetic field at this spot, right in the middle here, there's no, it's not generating any magnetic field right at the spot, so all the magnetic field's coming from wire 1, right? So wire 1 here is creating a magnetic field right at the spot of I2, and how much is it creating? Well, it's creating mu naught times I over 2 pi r. And then we have the sine of the angle between them, and well, let's see, L is going this way, and the magnetic field produced from I is going into the board, right? So they're going to be perpendicular to each other, so that's going to be sine of 90. And what's the direction going to be? Well, if the current's this way and the field is into the board, then that direction of the force is going to be sort of up, as I've drawn it, right? The force direction then is going to be, and maybe we'll get a different color for that, right? The direction of the force is going to be up because I is going this way. The magnetic field that's produced is going into, from the first current, is going into the board, right? So we have into the board magnetic field. We have current flowing this way. That gives an upward force, so toward the other wire, all right? And this, sine 90 is just 1, so we could write that force, maybe I'll write it in green here, right? What is that force per unit length? Well, that force per unit length ends up just being I prime times I times mu naught divided by 2 pi r, all right? So, and that then, of course, is also going to be the force from wire 2 on wire 1, and that one, right, the magnetic field from wire 1 is up at the, or sorry, from wire 2 is up at the spot of wire 1, right? And so we'll have up magnet, so we have L crossed with up. That gives, wow, hard to do this, but that gives a downward force, right? We also get that from Newton's third law, right? It should be equal and opposite. So the force will be downward. So these two forces, if the current's going the same direction, right, it's going to be an attractive force. They'll end up applying a force toward each other, all right? So I think that's sort of interesting that if you run current in two wires, right, in the same direction, they will attract each other. And this is actually something that you can demonstrate. And so I'll post a link to a video of a physics professor demonstrating this phenomenon. Of course, I should then note that if you instead you run current in opposite directions, right? If you run this current I this way and you run this current I prime this way, all right, what's going to happen, right? Well, there you're going to end up getting a repulsive force, right? The sign will flop, right? You flop the sign in one of them, you end up getting a repulsive force between these two, and you can sort of see that if you again draw on your magnetic field, right? Draw on your magnetic field, right? And here, but now here the magnetic field is going this way, right? So it's going into the page on the top, right? Into the page on the top and out of the page on the bottom, right? And now if we think about, so this field, it's going at this location, it's coming out of the page, right? So we have a magnetic field out of the page, and we have or sorry, into the page. X's are into the page, goodness gracious, right? We have a magnetic field into the page, and we have a current I, so we go current I cross magnetic field into the page. That gives us a downward force, right? Current I cross magnetic field into the page. That'd be a downward force, and so now the force would be this way, and this one would have to be equal and opposite. You'd get a force that way. All right. One other brief thing that I should mention about what's going on between these two wires, sort of an interesting thing, is you'll notice that in between the two wires where the current's going in the same direction, all right, the magnetic field from wire 2 here is going to sort of be canceling with the magnetic field of wire 1. Like here, magnetic field, it's into the page from this one, out of the page from this one. You know, they'll have different strengths, right? Over here, the one from wire 2 is going to dominate, so the net will be out of the page but weaker, right? Here, the net will be into the page but weaker, and somewhere in the middle, you know, if you imagine they had the same current exactly in the middle, these two would actually cancel out, and you'd get no magnetic field right in the center if you had actually the same current. In this case, though, all of the magnetic field in between is out of the page, so you actually end up with a really strong magnetic field in between, right? Really strong magnetic field in between because it's all getting added together, all right? And so here, actually, you know, there are 0 places, nowhere here is the magnetic field actually ever go to 0 because it just gets added together here in between. So, here you get this little equilibrium area where you actually get 0 magnetic field. That doesn't happen in the case where the wires are going in different directions. All right, well, hopefully this was a little bit helpful. It shows how we can combine what we've learned with Biot-Savart. Biot-Savart is all about wires creating magnetic fields. All right, with our force laws that ask how do moving charges respond to magnetic fields. So here we had a wire creating a magnetic field, right, and a wire responding to the magnetic field, and you can combine those together and see this cool effect in having multiple wires and what sort of forces, attractive or repulsive, end up happening between those wires. So I think I will leave it there. Good luck on your homework. Feel free to reach out to me. And I'll also post some demo videos that from other professors who aren't recorded them when they weren't in quarantine for you to watch with this as well. So, all right, thank you all.